96 hours, we illuminate the light to the tumor site, and then this tumor tissue can be treated. So, in contrast to the chemotherapeutic drugs, the photosensitizers are non-toxic to cells in the absence of light, as shown in this data, even at high concentration. When the photosensitizers in the ground state absorb an appropriate wavelength of light, it will be promoted to the singlet excited energy state, and then it may either revert to the ground energy state by producing fluorescent signal, or it may advance to the triplet excited energy state via intersystem crossing. When it is they are in the triplet excited state, they transfer their energy to the surrounding oxygen molecules, thereby producing cytotoxic singlet oxygens. These singlet oxygens react with the cellular components and induces apoptosis or necrosis of the target cancer cells. So as I mentioned, it is non-cytotoxic in the absence of light, but it becomes highly cytotoxic when they are exposed to the light. Interesting point is that one photosensitizer can generate multiple singlet oxygens as long as there is a supply of light from the external laser system. Since the photosensitizer is non-toxic to the normal cells, serious side effects can be avoided, and also functions of tissues or organs can be preserved after PDT in contrast to radiotherapy and chemotherapy. For example, women patients are able to get pregnant after PDT. Also, PDT induces no pain, only minor pain during PDT procedure, and since it is non-toxic to normal cell, it is repeatable. And also, it can be applied to the cancer patient when surgery is not possible. For example, if a patient has a cancer in a structure that cannot be removed surgically, PDT can still treat the site. And also, cosmetic outcome is very excellent. PDT kills only cancer cell but does not damage collagenous tissue structure. So, and then normal cell will repopulate to this space. So there will be no scar after PDT. And the cost is very low compared with the other chemotherapeutic strategy. And also, as I mentioned in the energy diagram, one photosensitizer can generate multiple fluorescent signal as long as there is an external supply of light source. Therefore, we can use this property for see and treat system. For example, we can detect the tumor site in real time from the near-infrared fluorescence imaging, and then we can directly treat the cancer cell by increasing the laser power in this, as shown in this picture. Photofluorine is the first generation photosensitizer which was approved in Canada in 1999. It is still most commonly used photosensitizer. Even though it contains 60 compounds, it was approved by FDA because it has very beneficial effect compared with chemotherapeutic drug. But one of the major problems is it has molar absorption coefficient of molar absorption coefficient of this photofluorine is very low at 630 nanometer. As you know, for the deeper tissue penetration of the light, we have to use near-infrared light, but at this wavelength, its light absorption coefficient is low. And second problem is, as shown in this chemical structure, it has hydrophobic structure, so water solubility is very low. So as a result, the tumor selectivity is limited, and also it shows unfavorable biodistribution. So it can be accumulated non-specifically in the skin or in the eye. So this accumulated PDT drug in the body can be reactivated by exposure to light. Therefore, patients should avoid exposure of skin or eyes to direct sunlight or in bright indoor light for at least 6 weeks until these photosensitizers are excreted from the body. As shown in this picture, when the patient was exposed to the sunlight, their skin is burned. So in the second generation photosensitizers, scientists try to develop photosensitizer with high molar extinction coefficient in the near-infrared region. When we compare the photoframe, their molar extinction coefficient was pretty much increased compared with photoframe in the second generation photosensitizer. One of the examples is meta-tetrahydroxyphenylchlorine, or other name is Foscan or Tempoframe. It has a high molar extinction coefficient in 652 nanometers, and it shows 200 times more effective than photoframe. But also, they introduced this meta-tetrahydroxyl moiety to increase water solubility, but it is still hydrophobic enough. Therefore, skin photosensitivity was similar with photoscreen, and people have to dissolve this photosensitizer in the mixture of polyethylene glycol and ethanol water mixture for clinical use. So second strategy is to make the hydrophilic photosensitizers to shorten skin photosensitivity. As shown in this second generation photosensitizer, they introduced the hydrophilic moiety to increase the water solubility. As a result, this photosensitizers becomes highly water soluble, but still have a high molar extinction coefficient in water, and the photosensitivity was decreased to less than 1 week. But we have to inject this photosensitizer at higher dose because they are rapidly excreted through the urine. So we have to inject a higher amount of photosensitizer to obtain the sufficient concentration of this drug in tumor site. So we may solve this problem by conjugating targeting ligand with the photosensitizer. So as you can see in this animation, when we inject this targeting the conjugate by intravenously, this conjugate will bind to the target cancer cell receptor, and some of them still absorb, non-specifically absorb into the surrounding normal cell, and some of them are still circulating in the bloodstream. So we have to wait until these unwanted photosensitizers are excreted through urine or via metabolism. Since some of the targeting ligand, such as folate or peptides, still have hydrophobicity, so this conjugate also can be non-specifically accumulated in the surrounding normal cells. So maybe unwanted phototoxicity to the normal cell could not be avoided even if we use this targeted PDT agent. We may solve this problem by encapsulating this hydrophobic photosensitizer into nanoparticles, and also by conjugating targeting unit, we may also improve the target cell specificity of this nanosystem. But in this case, the nanoparticle circulate in the bloodstream for a long time, so this may increase the background fluorescence signal for a long time, thereby diminishing the target tumor to background fluorescence signal ratio. So we try to develop activatable PDT agent, which is non-fluorescent and non-phototoxic in its native state. And when it reaches to the tumor site, it becomes highly fluorescent and highly phototoxic by the action of tumor-associated enzymes such as matrix metalloproteinase or cathepsins or redox system in cancer cell and low pH in tumor. So I will introduce some of the examples developed in my lab. In 2006, we report for the first time that the enzyme activatable PDT agent is useful for selective fluorescence detection and photodynamic therapy of cancers. Multiple photosensitizer was conjugated to the polylysin backbone. The polylysin backbone is enzymatic substrate. Also, after conjugation, this photosensitizers becomes non-fluorescent, non-phototoxic while in the blood circulation or in the normal tissues. And when it goes to the tumor site, the tumor-associated enzyme degrades the polymer backbone. Then it becomes highly fluorescent and phototoxic upon light irradiation. So we can use this system for the fluorescence imaging of cancer with high tumor to background ratio and the subsequent selective PDT of the cancer site. As shown in this picture, this fluorescence of this conjugate was specifically increased by cathepsin B enzyme. Also, tumor site could be imaged from the near-infrared fluorescence imaging. Also, therapeutic efficacy was obtained using this nanoconjugate. We then developed a photosensitizer conjugated polymeric nanoparticle for redox responsive fluorescence imaging and photodynamic therapy. As you may know, the glutathione concentration in cancer cell is pretty high than normal cells, especially it ranges from 2 to 10 millimolar, while the extracellular concentration of photosensitizer is glutathione is less than 5 micromolar. So we try to use this concentration gradient of glutathione as the switch of activatable system. So we conjugate multiple photosensitizers to the hyaluronic acid polymer backbone via disulfide linkage, which can be cleaved by the reducing agents such as glutathione. In the aqueous solution, this conjugate forms a self-assembly nanoparticle, as shown in this SEM picture. When this nanoparticle was treated with reducing agent, it shows dose-dependent fluorescence increase. Also, singlet oxygen generation was increased depending on the concentration of reducing agent treated into this nanoparticle. Also, the reactive oxygen species responsive activatable photosensitizing agent could be developed for imaging and photodynamic therapy of activated macrophages. So, as you know, reactive oxygen species generated in the activated macrophages play an important immune role. Important, this excess ROS are produced by activated macrophage cells in various pathogenic conditions, including atherosclerosis. Therefore, we assume that the excess ROS might be used for targeting and developing the macrophage targeted activatable theranostics. And also, according to the previous report, polysaccharide polymers such as hyaluronic acid could be depolymerized by reactive oxygen species. So, to use this concept, we conjugated again the photosensitizer with the hyaluronic acid by a non-cleavable linker, and then formed the self-assembly nanoparticle. It becomes non-fluorescent and non-phototoxic even upon light irradiation. So as you can see, fluorescence was significantly inhibited in the nanoparticle system. Also, singlet oxygen generation was also pretty much 16-fold decreased in the nanoparticle system compared with the free type of photosensitizer. When we treat this nanoparticle with the various reactive oxygen species, the 9-fold increase in fluorescence signal was observed in the peroxynitride treated sample. Also, singlet oxygen generation was increased 18-fold when this nanoparticle was treated with peroxynitride. So we then checked if this concept can be applied to the real-time detection of activated macrophage cell. We applied macrophage targeted nanoparticle to the activated macrophage and also free photosensitizer. And without washing the cell, we get the real-time near-infrared fluorescence image every 15 minutes. As you can see, in the nanoparticle treated system, we can see the location of activated macrophage cell from the fluorescence image. In contrast, this pre-photosensitizer treated cell, we cannot discriminate the location of the activated macrophage because of a strong background signal was generated from the extracellular space. Also, the activated macrophage was selectively killed in this system in the presence of light irradiation compared with non-activated macrophage cell or human dermal fibroblast cells. And also, this activator system could be prepared by combining plasmonic nanomaterials and photosensitizer. For example, gold nanorod has a strong surface plasmon absorption band in the near-infrared region and has absorption coefficient of 10 to the power of 4 fold to the 10 to the power of 6 fold higher than conventional organic dyes. So it can be used as the ultra-efficient energy quencher for the photosensitizer. So we expected by controlling the distance between photosensitizer and plasmonic gold nanorods, we can control the optical property of the photosensitizer. For example, when the photosensitizers are located on the surface of the gold nanorod, it becomes non-fluorescent and non-phototoxic, but when it is released from the gold nanorod in the tumor site, it becomes highly fluorescent and phototoxic. For example, when we conjugate the photosensitizer onto the surface of gold nanorod by a peptide linker, which is degradable by matrix metalloproteinase 2, it becomes non-fluorescent and non-phototoxic. But when the MMP2 enzyme degrades this peptide linker, it becomes highly fluorescent and highly phototoxic. We proved this concept in the cell study, MMP2 positive and negative cancer cell. Also, the formation of charge complex between the gold nanorod and photosensitizer can be prepared for making the activator system. So, in the in vivo study, we can discriminate tumor site after 1 hour of photosensitizer injection, intravenous injection, by using this activatable gold nanorod photosensitizer complex system. Also, the therapeutic efficacy was pretty much good using this system, as shown in this picture. Okay, this is the end of my presentation.
Thank you very much. Any questions?
the titer formed